فعنا الانترودكشن to vectors. زي ما تكلمنا the heart of linear algebra is two operations اللي هو we add vectors and we multiply vectors by constants. Okay, so vector addition, we add two vectors اللي هم vectors v and w, or we multiply them by constants then we add them. هاي العملية اللي هو إذا كان في عندنا vector خلينا نسميه vector v. Okay, ضربناه بكونستانت خلينا نسميه ألفا، وكان في عندنا vector another vector w وضربناه بanother constant اللي هو بيتا، هذا راح يعطينا new vector خلينا نسميه x. هاي العملية اللي هي نضرب الفيكتور بكونستانت وبعدين نجمعهم مع بعض بنسميها linear combination. فإحنا هون بنقول إنه x is a linear combination of the vectors v and w. Okay, why did we call it linear combination? Because there is no vector raised to power. يعني if you see here the power is 1, v is raised to power 1, w is raised to power 1. There are no vectors multiplied by each other. This is we call a linear combination of the vectors. If I ask you what's a vector is a set of numbers like this. V is a vector with two components. The first component is 1, the second component is 1. W is another vector, okay? It has two components. The first component is 2. The second component is 3. We call these column vectors. Column vectors because they are columns. Now we call these vectors two-dimensional vectors. Why do we call them two-dimensional vectors? Because they have two components. Component 1, component 2. If they have three components, we call them three-dimensional vectors. If they have four components, we call them four-dimensional vectors. In this example, if we multiply v by c and we multiply w by d, when you multiply a vector by a constant, you multiply each component in the vector by the constant. Okay, so the multiplication of c by w, or sorry, c by v, this will be c and c. Okay, the multiplication of w by d will give us 2d and 3d. So we multiply each component inside the vector by the same constant. Now when we add the vectors, we add the corresponding entries together. We add the first component to the first component. So this is c plus 2d. And we add the second component to the second component. So this is c plus 3d. Now, let's draw the vector v, which is 1 and 1. Okay, so this is the two-dimensional space. So here's 1 and 1. If we take this point, which is the intersection of the coordinates, and we connect it with the origin by a line. So this is the vector V. Now if we multiply V by 2, what happens? So 2V is equal to 2, 1, 2. So it is in the same direction, but it grows bigger. Right? So if we multiply it by 3, again, it will be in the same direction, but it will be longer. Okay, if we multiply it by a minus or a negative number, let's say minus V, it will be at minus 1 and minus 1. So CV lies on a line. So if we multiply a vector by a constant, it will be either in the same direction or in the opposite direction, okay? But it will move along a line. So CV is a vector, lie along a line. When W is not on that line, what do we mean by this? That W is not equal to some constant alpha times V. So when we say W is not on that line, we are saying that we cannot write W as some constant multiplied by V. Then their linear combination, CV plus DW, fill the whole two-dimensional plane. Okay. It's W was 2 and 3. So this is 2. V plus W. Now, if we multiply W by a constant, we will be on this line. If we multiply V by a W or V by a constant, we will be on this line. Now, how do we add vectors? Do you know how do we add vectors? We complete the parallelogram, right? This is V plus W. Okay, so it is this point. So if we multiply V and W by constants, then we add them, then their combination will be a point inside this two-dimensional plane. Okay. Dot product of V and W. This is the notation for the dot product. V dot W. Right? And the length of the vector V, this is the notation for the length. Okay, or sometimes we call it the modulus or the amplitude of V, which is the square root of the dot product of the vector V with itself. Now, for a linear system of equations, we can write the linear system of equations in matrix format in this form, where A is the coefficient matrix of coefficients, X is the unknown vector, and B is the known vector. The solution is X equals to A inverse B, and this is only when A is invertible. We will come to this later. Okay. So Column vector V has two components, V1 and V2. We say that this is a two-dimensional plane. It belongs to R2. So what is R2? R2 is the space of all vectors with two components. In this case, R2 is the XY plane. The whole of the two-dimensional plane is R2. If V has three components, V1, V2, V3, we say that this is a three-dimensional vector and it belongs to R3. So R3 is the space of all three-dimensional vectors, or the space of all vectors with the three components. If V has n components, let's say V1, V2 up to Vn, then it belongs to Rn. And we call it n-dimensional vector, and Rn is the space of all vectors with n components. Vector addition or subtraction, V plus or minus W. Let's say that we have two three-dimensional vectors, V and W. And here note that they have to be of the same dimension, which means we add vectors or we subtract vectors only if they have the same number of components. Okay, we cannot add a three-dimensional vector to a two-dimensional vector. We add three-dimensional vector to a three-dimensional vector. Okay, so they both have to be of the same dimension. Now, when we add them, we add the corresponding entries together. So we add V1 plus W1, or minus if we are subtracting, V2 plus W2, V3 plus W3. Now, if we multiply a vector by a constant, if you remember, I told you that we multiply each component inside the vector by the same constant. So if V is V1, V2, V3, and we multiply it by 2, then 2V is 2V1, 2V2, 2V3. And minus V is minus V1 minus V2 minus V3. Minus V plus V will give us the zero vector. This is a zero vector, not a scalar zero. This is a vector with all its components are equal to 0. So minus V plus V is equal to 0. So if it is three-dimensional vector, then minus V plus V will give us 0, 0, 0, which is the zero vector. Okay. Now, if V belongs to Rn, which means V has n components, and W has m components, W belongs to Rm, then V plus W is not defined. Okay, that's what I told you before. In order to add or subtract vectors, they have to be of the same dimension. So, in order to add V to W, V has to be in Rn and W has to be also in Rn. If m is not equal to n, which means that the vectors are of two different dimensions, then we cannot add them. Linear combinations of V and W is the sum of CV and DW. So if we have V is equal to 1 and 2, W is equal to 3 and 4, find linear combinations of V plus or V and W, which means that we have to multiply V by a constant, multiply W by another constant, then we add them. So here we multiplied V by C, and we multiplied W by D, then we added them. Okay. So here we say find V plus W, V plus W, we said we add the corresponding components together. 1 plus 3 is 4. 2 plus 4 is 6. Okay. Find V minus W. 1 minus 3 is minus 2. 2 minus 4 is minus 2. Find minus 2W. If we look at W here, W is 3 and 4. If we multiply it by minus 2, it will be minus 6 and minus 8. Do we have any questions? Yes, Mr. Safe, what's your question?
يعطيك العافية دكتور.
يا هلا.
دكتور راح يتم تسجيل المحاضرات؟
المحاضرة احنا بنسجلها الآن.
تمام.
تمام. Yasin, yes, this is the first lecture. Okay, so if U, V, and W are vectors in R3, what do we mean by vectors in R3? That means that U has 3 components, V has 3 components, and W has 3 components, as we see here. Okay, then all combinations C, U fill a line. That's what we said, right? If we multiply a vector by a constant, then it will be in the same direction, and we will be moving along a line that goes through the origin. Okay, so if we multiply a vector by a constant, we will be moving along a line. Okay, all combinations of CU plus DV will fill a plane. Okay, as we said about the 2-dimensional vectors U and V before. So if we take the linear combinations of 2 vectors, it will be filling a plane. Given that the U is not a multiple of V, which means that we cannot write U as some constant C multiplied by V. CU plus DV plus EW, which is a linear combination of the 3 vectors U, V, and W, will fill the whole of R3, given that U is not a multiple of V and V is not a multiple of W. Okay. Later we will call these linearly independent vectors. The 0 vector is on the line because C can be 0, right? We said that CV represents a line, right? So if C is equal to 0, then 0 times V equals 0, right? Which means that 0 is in the line, on the line. That's why we said the line goes through the origin. And again, we say 0 that is on the plane that fills, or 0 is in the plane that is the linear combination of U and V, because C can be a 0 and D can be a 0. This is an example where V is 110, W is 011. Okay. Now, what is their linear combination? What's their linear combination in the R3 space? Their combination is a plane, right? Because if you look at V and W, they cannot be written in terms of each other, which means that V is not equal to some alpha times W. So their linear combination will fill a plane in R3. Okay. Now describe that plane. If you look at this, this is the X coordinate. This is the Y coordinate. This is the Y coordinate. This is the Z coordinate. So if we multiply C times V plus D times W, we will get C, C plus D, and D. Is 0 on this plane? Yes, it is on this plane. If C is 0 and D is 0, then this point is on the plane. Is 1, 3, 2 in this plane? Yes, it is. If we look at the plane, the Y component is the sum of the X component and the Z component. Right? So if you look at this, 3 is 1 plus 2. Is this point on the plane? No, because 2 is not equal to 1 plus 3. Now, if you have V as 1, 0, and W is 0 and 1, so this is V, and this is W, right? Because V is 1 and 0, W is 0 and 1. Okay. So, if we multiply V by a constant C, then we will be moving on the x-axis, right? So, if C is 0, then we will be at the 0. If C is 100, then we will be here. If C is minus 100, then we will be here, right? So we will be moving along the x-axis. Okay. Same thing about W. If we multiply W by a constant, then we will be moving along the y-axis. Okay. Now, how about if we take a linear combination of V and W? That's multiplying V by a C and W by a D. Okay. Then their linear combination will be the whole of R2, the whole of the XY plane. Why? Because any point in the XY plane can be written as a linear combination of V and W. Let's say, now, the point 3 and 4. Can this point be written as a linear combination of V plus W? Ibrahim Ismail.
نعم دكتور.
Ibrahim, can you write the point 3 and 4 as a linear combination of V and W?
النقطة 3 4. أيوة.
We need to write it as a linear combination of the vector V and the vector W.
تمام. V بتكون 3 0 و W بتكون 0 4.
V is 1 0. So
تمام.
you're saying that the point 3 and 4 is equal to 3V plus 4W. Right?
بالضبط.
Okay. So how about the point -1 and 3? Let's see. Ahmed Hussein.
أيوة دكتور. ثاني.
Yes, can you write -1 and 3 as a linear combination of V and W?
أيوة but minus V or 3 W.
Minus V plus 3 W. Okay.
بلس عفوا حكيت all.
Any questions? If we look at those two vectors, V and W, if you add the components of V, what do you get? You will get 0, right? Because 1 minus 2 plus 1 is equal to 0. If you look at W, it's the same thing. If you add the components, 0 plus 1 minus 1 is also 0. Okay. Then the linear combination of those two vectors, the linear combination of them is CV plus DW. So if you multiply V by C, we'll have C minus 2C and C. If you multiply W by D, then it is 0, D, and minus D. If you add them, then you will get C minus 2C plus D and C minus 2D. If you add the components of this vector, you will have C minus 2C plus D and plus C minus D. Then you will have C minus 2C will go to 0, and D minus D will give us a 0. Okay. Here we have an example. It says if U, V, and W are three vectors in R3, what do we mean that U is in R3? What do we mean by that? Osama Dawood. Osama Dawood. Osama Ahmed Dawood.
موجود دكتور.
Yes. What do we mean when we say that U is in R3? Do you know?
No.
Osama, pay attention to the lecture. لؤي. لؤي عبد الإله. لؤي. لؤي is absent. همام.
نعم دكتور معك.
يا همام.
نعم دكتور معك.
What does it mean to say that U is in R3?
إنه دكتور الثلاث نظر متجهات بالثلاثة dimension.
Each vector has three components, right? Each vector of these vectors has three components. Then, Mati, شكرا. Under what condition the linear combination of U, V, and W will fill only a line? Fadi.
معك دكتور.
Yeah, Fadi. Under what conditions the linear combination of U, V and W will fill only a line.
دكتور ما بعرف.
أحمد إسماعيل.
دكتور مش متأكد بس أظن إذا كل واحدة منهم بس component واحدة لها قيمة.
We said that they will fill only a line if they are, the three of them are in the same direction, or if V is a multiple of U and W is a multiple of U, right? So the condition, fill only a line when U is equal to V is equal to W. Not only this, if U is equal to some constant times V, which is equal to some another constant times W, then their linear combination will fill a line. Under what conditions the linear combination of U, V, and W will fill a plane? It will fill only a plane in R3. This will happen if one of the vectors, let's say W, can be written as a linear combination of V and U. It's not only U plus V, it can be alpha U plus beta V. So if one of the vectors can be written as a linear combination of the other two vectors, then the linear combination of the three vectors fill only a plane in R3. Now, what's the space of all linear combinations of U and V? Now, the question that you'll ask yourself is this: can U be written as a linear combination or a multiple of V? Can we write U
No.
in terms of V? No, because here
The second
there is
component.
no multiple of 0 will give us 1. Right? There is no multiple of 0 will give us 1. So U and V cannot be written as multiples of each other. This means that the linear combination of U and V is not a line, it is a plane in R3. Okay, what a plane is this? It is the XY plane. Look, because this is the X component, this is the X and the Y component. The Z component is always 0, right? Because if we multiply 0 by any number, it will be 0. So 0 plus 0 is 0. So here we have the Z component is always 0, but we will have the X and Y component. So this is the X and Y plane. Okay, in R3. So if U belongs to R3 and V belongs to R3, all linear combinations of U and V is a plane. U is parallel to V, right? Unless U is parallel to V, or U and V are on the same line, or as we said before, U is multiple of V. Now, here we have U, 1 and 2, V is a 3 and 6. So what's the linear combination of U and V? The linear combination of U and V is a line. Why is it a line? Because if you look at V, it is 3 times U, right? So U and V are on the same line. So their linear combination is not a plane, it is a line. Now, if you look at this U and V, they cannot be written as multiple of each other. So their linear combination will fill a plane, right? This plane is the XY plane. So their linear combination will fill the whole of R2. What do you mean that by the linear combination of U and V will fill the whole of R2? It means that any point in R2 can be written as a linear combination of U and V. So this is V, it is 0 and 1. This is U, is 1 and 0. Any point in this XY plane can be written as a linear combination of V and U. In this example, it says if U plus V is 4, 5, 6 and U minus V 2, 5, 8, find U and V. So if you add these two, here we have U plus V equals 4, 5, 6. U minus V equals 2, 5, 8, right? So if we add this left side, U plus U is 2U, V minus V is 0, so this is equal to 4 plus 2 is 6, 5 plus 5 is 10, and 6 plus 8 is 14. If 2U is 6, 10, and 14, then U is 3, 5, and 7. Okay, now if we know one of them, then we can know the other from these relationships, right? So we can say that V is 4, 5, 6 minus U, and we already know U. So this is 4, 5, 6 minus U, which is 3, 5, 7. So this is 1, 0 minus 1. Any questions? Lengths and dot products. As we have seen, a vector has a length and a direction. The direction can be defined as the angle it makes with the horizontal axis. Okay, so it has a length and a direction. First, let's talk about the dot product of two vectors V and W. We write them as V dot W. The way we do the dot product is we multiply the corresponding entries, then we add them. So V1 times W1 plus V2 times W2. Okay, so this is the dot product of the two vectors V and W. If you notice, this operation is commutative, which means that this is equal to W dot V. So V dot W is equal to W dot V, and it's equal to W1 V1 plus W2 V2. So if we do the dot product for these two vectors, so V dot W is equal to 4 times minus 1 plus 2 times 2. So it's minus 4 plus 4 equals to 0. We will learn in a minute that if the dot product between two vectors is 0, that means the vectors are perpendicular to each other, or that the angle between the two vectors is 90 degrees. Okay, so if the dot product, or sometimes it is called the inner product, between two vectors is 0, then they are perpendicular, or that the angle between them is 90 degrees. Okay. The length of a vector u, okay, this is the notation for the length of u. It's equal to the square root of the dot product of the vector with itself. Okay, so it is the square root of the dot product of the vector with itself. So if this is u, and we need to find the norm of u, we call it the norm, the modulus, the amplitude, they are all the same thing. So it is the square root of u dot u, which means that the first component is squared plus the second component is squared plus the third component is squared. Norm of u is always greater than 0. Why? Why is the norm always greater than 0?
لأن اللينث ما بصير يكون قيمة سالبة.
Because it is a length, right? Because it represents the length. The length cannot be negative. Okay? If the norm of u is equal to 0, this means that all components of u are zeros. That's the only case when the norm of u is 0. So the norm of u is 0 if and only if all components of u are zeros. Now, the norm of alpha times u is equal to the absolute value of alpha multiplied by the norm of u. Can we prove this? If I ask you to prove this, can you do it? So if you belongs to Rn, and we need to find the norm of alpha times u. This means that we are looking for the square root of alpha u1 square plus, sorry, alpha square u1 square plus alpha square u2 square plus alpha square u3 square plus till we reach alpha square un square. Now this can be written as alpha square times u1 square plus u2 square until we get to un square. Now this is equal to absolute value of alpha times the norm of u. Why did we take the absolute value of alpha? Because we said the norm cannot be negative, right? The norm is always positive, so we have to take the absolute value of alpha. Now, if the length of u is 1, then we call u a unit vector. So a unit vector is a vector of length 1. Okay? So if the length of the vector is 1, then we call this vector a unit vector. Then, if we have this example, if u is 1/2, 1/2, 1/2, and alpha, and it belongs to R4, it says find alpha such that u is a unit vector, or the norm of u is 1. Now we know that the norm of u is the square root of 1/4 plus 1/4 plus 1/4 plus alpha square, right? And this is equal to 1. Now we can write it as 1 equals to 3/4 plus alpha square. Or we can say that alpha square is 1/4. Then alpha is equal to plus or minus 1/2. Okay? If V is not a unit vector, then the vector W, which is equal to V divided by the norm of V, is a unit vector in the same direction as V. Which means that we can make a unit vector from any vector. How do we make a unit vector from any vector? By dividing the vector by its norm. Okay? So if we have this vector is V, then if we multiply V by the norm of V, then we will get W, such that the norm of W is equal to 1. If you look at W, the norm of it, or its length, is 1, but it is in the same direction as V. Okay? Can we prove this? Can we prove that W is a unit vector?
Yes.
How can we prove it, Yasif?
أول إشي لما أجي أطلع النورم لل V على نورم ال N لازم يكون بيساوي النورم لل W ويساوي 1.
If we want to prove that W is a unit vector, then W dot W must be equal to 1. Right? So if we take W dot W, this is V divided by the norm of V dot V divided by the norm of V. Okay, then we will have this V dot V divided by the norm of V square. V dot V is equal to the norm of V square divided by the norm of V square, and this is equal to 1. Okay. Any questions? This is an example. If we have V is 1, 1, 1, then the norm of V is the square root of 3. If we want to make a unit vector in the direction of V, then we will have to divide V by its norm. So V divided by the norm of V, which is 1, 1, 1, divided by the square root of 3, then this is equal to 1 over square root of 3, 1 over square root of 3, 1 over square root of 3. Now, here it says if U is 1, 2, and alpha, and the norm of U is the square root of 6, then find alpha. This is kind of easy question. So the norm of U square is 1 plus 4 plus alpha square is equal to 6. Then alpha square is equal to 1, or alpha is equal to plus or minus 1. Any questions? So now the angle between two vectors. If we have two vectors, V and W, and we want to find the angle between them, which is theta. Okay, so cosine alpha is V1 divided by the norm of V. Since this is V, so this is V1 and this is V2. So the cosine is V1 divided by the norm of V, okay? And the cosine of beta, where beta is the angle that W makes with the horizontal axis. Again, this is W1 and this is W2. So the cosine of beta is W1 divided by the norm of W. And these are the signs, of course. Sine alpha is equal to V2 divided by the norm of V, and sine beta is to W2 divided by the norm of W. Cosine theta, which is, again, if you look at theta, theta is the angle between W and V, and it is equal to beta minus alpha, okay? So cosine theta, which is cosine beta minus alpha, and we know from the identities that cosine beta minus alpha is cosine beta cosine alpha plus sine beta sine alpha. So if we take these equations and substitute them into this equation, then we will have that cosine theta is V1 W1 over the norm of W norm of V plus W2 V2 over the norm of W norm of V. So again, if we simplify it, it will be V1 W1 plus V2 W2 over the norm of V times the norm of W, and this, the numerator, is the dot product of V and W. So cosine theta, theta is the angle between V and W, is equal to V dot W divided by the norm of V times the norm of W. So I think you may have seen this before. We can write V dot W as the norm of V times the norm of W times cosine theta, where theta is the angle between V and W. Now, if the vectors are orthogonal, and we say that they are orthogonal if the dot product is 0 or the angle is 90 degrees. If V and W are unit vectors, so if they are unit vectors, then the norm of V is 1, norm of W is 1, then cosine theta is V dot W. Zero vector is perpendicular to any vector, right? Why is that? Because the dot product of the zero vector with any vector is 0. Now, if the dot product between the two vectors is positive, is greater than 0, that means if we look at the quarters, we have 4 quarters. The cosine is positive in this quarter. It is negative in this quarter, right? It is again negative in this quarter and positive in this quarter. This is cosine theta. So if the dot product is greater than 0, and if you look at this equation, the denominator is always positive. So the sign of the cosine theta depends on the sign of the dot product. So if the dot product is positive, then the cosine is positive. If the dot product is negative, then the cosine is negative. So if the dot product is positive, that means we are in the first quarter, which means that theta is between 0 and 90 degrees. If the dot product is negative, that means we are in the second quarter, which means that the angle is greater than 90 degrees and less than 180 degrees. So theta greater than 90 degrees or less than 180 degrees. Again, okay. Then